Hi, welcome to another lesson at Edu Solutions Institute. Today we will be looking at the IB Physics syllabus, and we will be continuing with our syllabus, looking from our previous lessons where we looked up to inclined plane to now we'll be looking at circular motion. Now, circular motion is in essence a type of motion that is around a curve, and it's not within a straight path or a linear path. So circular motion has to do with objects going around a specific curve. Now, in this type of motion, we have some unique terms that we need to cover throughout this course. Now, the first term that we're going to look at is called a radian. What exactly is a radian? Now, if we define a circular distance in terms of circles, then the distance around a circle is called a circumference, which we know is 2 pi r. Now, how many radians are there in this 2 pi r, just one circular motion? And this is where we know that 2 pi radians gives us a total one circular path motion. So therefore, what we know is that 360 degrees of a circle is equivalent to 2 pi radians in circular motion terminologies. So 1 pi is just half of a circle, which is 180 degrees. 2 pi is 360 degrees, all right? And it continues like that. If the radius changes, it's still the same angle that we have to cover in order to make the circle complete. Then we look at the timing for this circular motion. To go around a circle one complete time, or a one revolution, or one oscillation, we say this time is uniquely called the period. And the period is the time to complete that one revolution, that one oscillation around a specific circle. Right? Then we look at a term called angular velocity. Our previous lesson in linear motion, we look at linear velocity, which is a v. Now in angular circular motion, angular velocity is represented by the omega sign, which is that unique W there from our Greek symbol. And what this is, it's the angular distance that's traveled over the time it takes to travel that distance. So remember, we know that for a complete circle, its distance that it traveled is 2 pi. And if we divide that by the t, which is a periodic time, which is a capital T, then we get that omega is 2 pi over t. So omega, in a sense, is the speed or velocity that the object has while going around the curve. Right? So it's different from an object moving in a linear path, which is v for linear velocity. Here is an example that says a Ferris wheel takes 40 seconds to make a complete revolution. What is its angular velocity? And its angular velocity is just a 2 pi because it's 360 of a degree to make the circle. And it's divided by the time it takes to make one circle, which is 40 seconds. And we get 0.157 radians per second. And that's the unit for angular velocity, right? So linear velocity was meters per second, because meter was the distance traveled in linear motion. In circular motion, distance traveled is measured in radians. So it's 0.157 radians per second. Right? We still will look at the term linear velocity, because even though objects are going around a circle with a circular curved velocity, it still at points have its linear velocity. And these linear velocities are tangent to the circle. So as you can see this circle here, and in this first, each time this card goes any point around this circle, it's actually pointing in a linear path. So therefore, those red arrows show the linear velocity at each individual point of the circle. So to find those straight velocity before it starts to turn, It's called the linear velocity. And that linear velocity is simply put the distance over the time, and the distance is 2 pi r over the time, which is a periodic time t. And hence, if it's 2 pi r, right, and we know that 2 pi over t is omega, then our linear velocity can be linked with angular velocity, which is v is equal to omega r. Right? Now that we know some unit terms, let's go into a little bit about centripetal force and acceleration. Now, according to Newton's first law of motion, which is called the law of inertia, that tells us that if you're moving with a constant velocity in a straight line, unless acted on by an unbalanced force, or if you're at rest, you'll remain at rest unless acted on by an unbalanced force. Right? Now, objects going around a circle will exhibit what we call a centripetal acceleration, which is due to the change in velocity and its direction. Now, the linear velocity does not change for an object going in a constant circle, but its direction changes repeatedly. So because there is a change in direction, then that means we have a change in velocity. Because if it's going direction 1, which is a positive velocity, and then it goes to direction 2, which is a negative velocity, there is a change in direction, hence there is a change in velocity, hence we have an acceleration. So to find acceleration, centripetal acceleration, it's always v squared over r as a primary unit, our formula that we use to calculate this specific velocity. Now, the direction in which this acceleration is going is dependent on the direction that the centripetal force is going. And it's always primarily going towards the center of the circle, right? So because acceleration is going towards the center, that's because the centripetal force is going towards the center. And what exactly is this centripetal force? This centripetal force is the force that is needed, or it's the resultant force that is created based on objects going in a circle. So it's a resultant force that keeps the object going in a circle. And we find this force by multiplying the mass times the linear velocity squared divided by the radius of the circle. And what this tells us is that the centripetal force is dependent on the mass of the object that's going in a circle, the speed that the object is going at, as well as the radius that the circle has. Right? We also could simplify this formula and tells us that the centripetal force is equal to the mass times omega squared times r. And remember, omega is the angular velocity. Right? Here is a use of the formula. If we have a 3 kilogram rock swings in a circle of radius 5 meters, if its constant velocity is 8 meters per second, what's the centripetal acceleration and its force? So we're given the linear speed, the radius, and the mass. So to find the centripetal acceleration, it's v squared over r. So it's 8 squared over the radius of 5, which we get 12.8 meters per second squared. And then to find the force is always based on Newton's second law of motion, m times a. Because the a is already v squared over r, so we don't have to calculate that again. We just multiply the mass, which is 3 times acceleration, which is 12.8. So we get a 38.4 newtons in centripetal force. Right? So this actually tells us that objects going in a circle will always experience a force, which is called a centripetal force, which is a resultant force due to the action of other forces creating that circular effect. Now, in circular motion, we have different types of circle. which we can classify as a horizontal circle or a vertical circle. Now, in vertical circles, as the image here shows, let's say we attach an object to a string and we're creating a circle right in front of our face. So at individual points of this circle, there are unique happenings that's occurring at different points. Now, at the bottom there at point C that's highlighted, the tension of the string is going up towards the person's hand, towards the center of the circle. The weight of the object is going down. So therefore, the centripetal force would be the tension minus the weight. That gives us the centripetal force. And that's because it's a resulting force. At the top, at point F, the weight is going down, just like the tension always going down towards the center of the circle. Hence, your resultant force is that centripetal force is equal to the weight plus the tension force, because they're going in the same direction. All right, so what we know from here as well is that the tension force is always the lowest at the top of a vertical circle, and it's always the maximum at the bottom of the circle, because at the top it's the lowest because it's going in the same direction as the weight. So there is a small to minute tension in the string, and at the bottom it's going opposite to the weight. So the weight is pulling it down, tension is trying to pull it back up, so hence you get the maximum force or tension. Right, so that's what we just learned in terms of your centripetal force in terms of vertical circles. Right. Now, vertical circles can happen on a surface as well. Example, a roller coaster. Now, in this case, we do not have tension, but what we know is the relationship between the forces that are reacting. So in this case, the roller coaster is touching the bottom of its track. So hence there is weight going down, as well as there is a normal force pulling it up. Because remember, once two things are in contact, there will be a normal force generated to oppose that applied force. So the applied force is the weight, and hence the track is pushing back up on the cart with the persons there with a normal force. And hence we know that the net force is the normal force minus the weight of the object. And that net force will be your centripetal force. Right? So at any point when the cart reaches the top here, so it's going down in a curve more than going up, then that means your weight is going down and your resultant force, not your resultant, your normal force is going up. And again, we minus them because they're going two different directions, and that gives you the net force, which is your centripetal force. Now, if you notice here, the net force is 1,337 on the top of the track, and when it's at the bottom of the track, it was 4,462 newtons. Right? So that tells us that on the bottom of this track here, there is a greater centripetal force than when it's at the top. Right? Because when it's up here, it requires a great force in order to keep the momentum to carry it up the curve. But when it's at the top of the curve, it doesn't require a lot of force to keep it because it's now going down, aiding with gravity. All right? So that is how we perceive circular motion in terms of vertical motion when we have a tension, or when it's no tension is present. All right, the final circle we're going to look at is more of a horizontal circle, like in this case. Now, if you notice, there is a barrier, persons are on the sides of this barrier, and it's going to turn in a horizontal platform. Now, the weight of the persons are going down, that's noted by FG. There's frictional force actually is going up. Why? Because the frictional force, when it's turning, it's trying to keep the object going opposite to its motion. So the persons in this case, weight will be pulling them down, so friction is pulling them back up. And hence, your resultant force is always towards the center of the circle, right? So that is your R, which is represented by your normal force as well. So to find your centripetal force, sorry, it would be the value that R is. And because the persons are not moving, we know that the frictional force will be equal to the weight of their gravitational pull, right? So based on the type of circles, we will have to generate a specific relationship between the forces that are present in order for us to find the centripetal force. So that's it for us today, guys. Hope you understand a lot more about centripetal force, and I'll see you next week where we continue to learn about the IB physics syllabus. Thank you.